Hello everyone, I'm Jing, an upcoming third-year PhD student in University of Nottingham, Ningbo, China, supervised by Dr. Heng Yu. Today I'm gonna present FiDRL, Flexible Invocation-based Deep Reinforcement Learning for DVFS Scheduling in Embedded Systems, which will appear in IEEE transactions on computers. And firstly, let me introduce the background and the challenges of this work. Dynamic voltage frequency scaling, short as DVFS, is a popular technique in terms of power and energy management of many electronic devices to achieve their longer battery life and make them energy efficient. The main idea of DVFS is to dynamically adjust voltage and frequency of processing codes according to their workload and system indicators. Reinforcement learning, especially deep reinforcement learning, short as DRL, has shown its superiority in decision-making optimization without expert-based knowledge and adaptive for new environments. The DRL agent gradually learns optimal DVFS scheduling policy to achieve energy minimization or energy efficiency by interacting with the processing core with many voltage and frequency settings based on some system states. As FiDRL-based DVFS brings a lot of attention in the embedded system community, many works contribute to use DRL in the standalone embedded system. But the whole embedded system, which used to be the applied environment in DRL process, is different from the normal applied DRL environment. Let me introduce a concept first, called agent invocation. It means the inference process itself when the agent making the decision. For example, neural network is used to be the agent in DRL. The network inference is the agent invocation. So the contradiction and the research gap here is that in normal applied environment, the agent invocation has no cost, which means it cannot change the state of the environment. Only the action made by the agent causes state transition. However, there exists agent invocation cost in a standalone embedded system, where the agent is a part of the whole system. So the agent invocation can change the state of the whole system. According to this insight, here we provide two motivational examples. The left one indicates that the agent accounts for around 10% of the overall energy consumption when using DRL-based DVFS to optimize the energy consumption. This part of energy always happens in such embedded system, but not appear in the normal environment. This phenomenon shows the invocation cost influence the effectiveness of DRL and has potential reduction opportunities. The right one is an example decision sequence in DVFS scheduling. The right points are the same decision, which does made by the agent, and the cost such as the network inference energy happens in the system. So we ask how to design a flexible or the agent invocation cost-aware DRL framework and use it for DVFS scheduling in the embedded system to reduce its energy consumption. To solve this question, the first and main challenge is how to design such flexible DRL and reduce the invocation cost to the whole system, because the actual cost of the agent making the whole system suboptimal. We need to make the framework be aware of this and verify its effectiveness when taking the agent as a part of the environment. In terms of using DRL to help DVFS scheduling, the next challenge is how to formulate this kind of DRL-based DVFS to reduce the overall energy consumption. We need to think about a general way to adapt different kinds of devices or tasks. Another challenge is to train the DRL-based DVFS. Only simulated systems do not reflect practical hardware platform. We should think about a practical way to well-train the agent, because normal training way causes inaccuracy, as the left figure shows. The learning process of the agent influences the next observation of the environment, which means the training 1 process influences the next observation, which is observation 2 here, making the training not perfect. Some related works were conducted in embedded system community and AI community, but the unsolved issues commonly contain the lack of awareness of our mentioned challenges, and some works from AI community is not designed for the embedded system scenarios and brings some concerns when simply transferring their solutions. To solve these 3 challenges, we propose a flexible invocation-based DRL. We use FiDRL in the following description. So firstly, to reduce the agent invocation cost and its impact to the whole system, we design a flexible invocation scheme. Start from the objective we want to achieve, which is E total, means total energy, and the E task is the energy caused by running tasks. E agent is 1 invocation cost. So during T times of agent decisions, E agent is always here. To mitigate this implicit cost, we should find a way to reduce T while keeping the performance. The idea is that we need to temporarily reduce the invocation of the agent. So we need to extend the action space, making it not only contain the actual action that the agent takes, but also contains the decision period that the agent applied for the action. To make things more specific, we define the A flexible, which is a new action including the original actual action taken by the agent, which is A original, and the A interval means how long that the A original will take. And A interval could be either discrete and continuous, depending on the way of usage. We also provide a convergence analysis to prove that this kind of extension is valid and effective. The detailed proof can be found in our paper. After the designed theoretical framework, we use our FiDRL to formulate DVFS scheduling, and we introduce 2 kinds of different DVFS schedulings first. Here is a sample case study using our FiDRL-based DVFS. The intra-task DVFS means the voltage and frequency adjustments happen after the task ends and before another task starts. The intra-task DVFS is that the adjustment happens during the task execution. And from the picture, the height of the rectangle is A original, which is the voltage and frequency applied for the processing core, and the length of the rectangle is A interval. We can see the decision interval can be flexibly changes different from the conventional DRL methods. According to this, FiDRL can avoid repetitive decisions and reduce the invocation cost. Specifically, the optimization goal is to minimize the energy consumption of the system, given adjustable voltage and frequency levels. In terms of FiDRL, the action is to choose different VF levels and its applied intervals. The states are combined with some general signals including system temperature, average power consumption, and the previous action. The designed reward is the energy consumption of the system, with the factor to normalize and stabilize the learning process. Next, I will introduce the whole system workflow and the training mechanism. Since on-device training will interrupt the continuous observations of the agent, we propose a hybrid on- and off-chip training mechanism. We use the on-device agent to collect the training data, sending them to the off-chip training machine. After training, we send the update network parameters back to the embedded device and start the next round of training. This kind of method utilizes the off-chip training resources and provide on-device real inferential data, making the complete training process accurate and effective. We implement the modular components on a heterogeneous embedded platform. For inter-task DVFS scheduling, we synthesize processing units on FPGA, and for intra-task one, we use the CPU to process the task. The FiDRL is customizable and synthesized on FPGA, and the system monitor could be used to detect required system signals, then input them to the agent. The agent will output the voltage and frequency suggestions, drive the corresponding DVFS controller to regulate. With this kind of implementation, we can customize different components according to our requirements. Next is our experimental results. For the experimental settings, we use Xilinx DCU-104 as the hardware platform and a Linux PC as our training machine. We conduct several inter- and intra-task benchmarks, including various network accelerators and basic applications in Splash 2. As our compared methods, we use a simple execution without DVFS as our baseline, plus 4 different methods including heuristic-based, normal DRL-based, and temporal DRL-based DVFS. They are from either embedded system or AI community. Here are the overall results. We can see the right labels, which is our method. It could averagely reduce 23.3% system overall energy and 55.1 agent energy compared to the corresponding baseline. Our method achieves the most overall and agent energy reduction among all methods. Additionally, there is a green label, which is the work from the AI community. It also shows the temporal features of DRL, like reduce the repetitive decisions. We implement the idea on the embedded system, and it also shows 11.5% agent overhead reduction, achieves the second best result. So we further evaluate the work from the AI community. We call it temporal. We found the reason that is different from our FiDRL. It is a two-network architecture. The state used in net 1 to output the actual action A, and reused in net 2 to output the repeat times J. So the state is reused here, but in embedded system environment, the states are different before and after passing net 1. And the network architecture is not compact in embedded scenarios. So we also test 2 modified versions of temporal. One is make it lightweight spatially, such as using pruning, and another is to make the state reobserved before passing the net 2. The result here shows our FiDRL outperforms them due to their not compact architecture and accuracy loss that pruning takes. Back to our FiDRL, one thing to notice is 2 parameters which determines the upper and lower bounds of the decision interval. We evaluate different ranges of interval settings and use gray search to sweep possible combinations of different ranges, and we could find optimized settings in this way. We also test the stability of the learning process, showing that FiDRL has better training performance, and we compared the temperature with the thermal management work and record hardware resources utilization with other works. Our FiDRL demonstrates stable temperature variation, and the hardware resource utilization is similar with normal DRL implementations. Well, let's summarize the whole work. To design a flexible DRL framework for DVFS scheduling in a standalone embedded system to reduce energy consumption, we proposed FiDRL, solving the temporal overhead of the agent invocation and its impact to the whole environment. We formulate FiDRL to the DVFS scheduling for energy optimization on embedded system featuring both inter and intra-tasks. And finally, we give the whole integrate FiDRL-based DVFS system equipped with a hybrid on and off chip training mechanism for feasibility, verification, and customizable settings. Here are all the references. Thank you for your attention.